It's my pleasure to welcome Professor Danial Faghihi today for the Colloquium. Professor Faghihi did his PhD at Louisiana State University on non-local methods for gradient plasticity, and then he was at the Oden Institute for multiple years as a postdoc where we overlapped, and he has been a professor at University of Buffalo in the Department of Mechanical and Aerospace Engineering, and he's the recipient of the NSS Career Award, and with that I'll let you take the stage.
All right, thank you very much. Before I start, I want to sincerely thank Dr. Buklas and the rest of the camp community for their kind invitation and the opportunity. I had a great visit, especially the lunch with the students, and thank you all for taking the time to attend this presentation. Today I'm going to talk about the strategic selection of optimal predictive model for making decisions in the face of uncertainty, and this is the collection of my focus and interest over the last 4 years and a little bit viewing into the future. Most of these works are done by recently graduated PhD student. He is actually sitting here now. He's part of the Cornell, Jin Tan, or he also goes by Kira. All right, so the motivation of this talk is computational prediction of complex physical phenomena. Now we have tremendous opportunity to harness large scale data from imaging, measurements, high fidelity simulations, integrate those into computational model to predict future state of physical systems, complex physical system, and use those predictions for making high consequence decisions about these complex systems. A few examples of my past and current projects include for predicting plasma fusion reactor operator, for example, for clean energy, or leveraging microstructural image to advance the nano manufacturing of materials, or leveraging MRI data for predicting the future development of tumor and optimizing the treatment in a specific patient in terms of precision medicine, or finally using predictive models for design of high performance insulation component for net zero building to contribute to the climate change. In all these applications, we either use the physics-based models, which by physics-based I mean mostly normally a set of PDEs that we solve with finite element, or for larger scale problem, we create a surrogate model based on scientific machine learning models to basically to gain computational efficiency. But the main challenge when it comes to physical system is that our data is always limited, is uncertain, it's sparse in temporal or spatial, that poses issue in the reliability of our computational prediction. And the key enabler for making reliable prediction is to validate these models in the face of uncertainty in data and model error. A specific challenge about predictive modeling and model validation in general is the choice of model itself among all possible models that we construct for a particular problem. A few examples in physics-based models, continuum mechanics, we need to make the choice of constitutive relations among all possible relations that satisfy the second law of thermodynamics. Another example, coarse graining of atomistic system. We face the choice of different mapping from atomistic topology to the coarse grain system, and then what type of interatomic potential we need to use. This leads to a large family of possible models with different fidelity and complexity. The situation is far more complex when it comes to machine learning models. There is no predefined rule to determine the number of layers or connections in deep neural net, or the arrangement of different layers in convolutional neural networks. Domain scientists, they make their physics-based modeling choice based on their experience, extensive experience about a particular material, particular process. And most of the architecture selection in neural networks, as far as I know, is based on looking into some performance on the testing set, or sometimes handcrafting the architecture by some experts. While all those expertise and experience must be taken into account, if our goal is to make a reliable prediction of complex physical phenomena to making decisions, then we need a systematic approach to select the model that we use for our prediction. This brings me to the outline of the presentation. I start with some mathematical preliminaries to basically set the stage in terms of notation that I'm using throughout this presentation. Then I talk about Occam-Plausibility Algorithm, a class of strategies for systematic validation and selection of predictive models, either for physics-based model or scientific machine learning-based surrogate model. Then I discuss some scalable way to do Bayesian inference and filtering, basically integrating data and model by Bayesian inference. In the case that we have high-dimensional data imaging, high-dimensional parameter space, for example, especially varying parameters. And I touch base a little bit on how we use these predictive model coming from validation, selection, scalable Bayesian inference, to making decision under uncertainty, design and control decision under uncertainty that requires solution of an optimization that's under possibly high-dimensional uncertainty as well. And I conclude that how these methodologies, how these frameworks, fancy computational approach, how they come together to build a foundation toward predictive digital twins, towards application across science, engineering, and medicine. All right, so let's start with some mathematical preliminaries. I define my model set as a strict M. It consists of a set of possible models, parametric model, M1 to MP, each depends on a set of parameters, theta 1 to theta p. And then I write my Bayes theorem to determine these parameters as for given observational data. This is a conditional probability. And I use prior knowledge on the parameters, the choice of noise model to construct the likelihood function to get to my posterior. Of the parameter given observational data, as you see, I write these probabilities explicitly depending on the model itself, model set, and the scenario in which we are implementing this model. And scenario is extremely important when it comes to model validation, and as I will describe. All right, the point estimate that maximizes the posterior known as math, and the denominator of Bayes' rule is known as evidence. It's the probability of observing data. In classical Bayesian setting, we normally throw away the evidence. We say that this is a normalization factor. But if we rearrange the Bayes' rule, it turns out that evidence consists of posterior mean of log likelihood and relative entropy between prior and posterior. Basically, the evidence of a model expresses a trade-off between how much the model fits the data and the amount of information we gain about the parameter when the data arrive. And in a simple setting, in a 1D, in a classical paper of McCain, if we have two different models, one of them is very simple, M1, that can make a prediction in a very limited range, but with a high probability. While we have another model that might be more complex because of having more parameters, can provide wider range of prediction, but in lower probability. To make this evidence as a measure for model comparison in a more systematic manner, we look at it as a new likelihood in the Bayes rule, now writing it over all the model in the model set. Basically, by having the prior knowledge on the model in the model set, we use this evidence to compute the posterior model plausibility, and in a set of competing model for a given set of data, the model that has largest rho I basically is deemed the most probable. All right, so these are the basics. Now, how we can use this model evidence in more practical sense. Technically, if we have 100 different models, we cannot compute evidence for all of them, right? And our goal, again, goes back to prediction. Our model selection strategy is based on Occam-Plausibility principle. It's a problem-solving principle. It says that basically, in a nutshell, if you have multiple theories for solving a problem, the simplest one is the best. And we translate that to the fact that when choosing among a set of possible models, the optimal choice has three characteristics. Should be simple, that is based on a subjective measure of model complexity. It can be number of parameters, it can be based on numerical mean. It should be valid, that should pass the validation test, Bayesian validation test that I discussed shortly. And we ensure the predictive ability of these models by design of model-specific validation experiment that reflects the structure of the target prediction or quantity of interest. So what we are advocating here, instead of just grabbing whatever data for validation, validating the model, instead you need to focus and design the specific validation data for that specific model to be effective, to make the prediction possible. All right, putting these together leads to a strategic selection. Now I'm showing you the physics-based version of it. Occam-Plausibility Algorithm, or OPAL, consists of identified set of possible models, categorizing them based on the level of complexity. We start with the lower category, simplest model. We do Bayesian calibration, compute plausibility, design the validation experiment, and if that model passes the validation test, that's the optimal predictive model. Otherwise, we go to the next category and make it more complex as we move along. All right, let's look at this as in a very simple example. The idea here is that we want to predict the deformation of these polycrystalline macroelectromechanical devices under applied load. It's a polycrystalline metallic materials, and basically we are considering plastic deformations. And the idea is that we have two modeling approaches. One of them is high fidelity, based on discrete dislocation dynamics. It's a high fidelity, but very limited. It cannot account for all this complex macrostructure. We use that to generate data to calibrate, inform, and validate a continuum strain gradient plasticity that is a lower fidelity in the continuum level. We can do finite element models for this complex system. All right, so just as a quick view of a strain gradient plasticity, if you guys are not familiar with continuum mechanics, that's fine. This is basically two sets of PDEs that we are trying to solve. And after substituting the constitutive equation, this is the second PDEs. That you see that it consists of four different terms. For mechanics people, you might remember 10, 20 years ago, there was a big fight in the strain gradient plasticity. Some people saying that this term is not required. The other people believe that the other term is not required. So what we are doing here is the model agnostic approach. We construct 6 different submodels of this full model based on turning on and off different terms, and then we use the data to select the optimal predictive model for us. All right, so another thing for implementing OPAL that is extremely important is the notion of scenarios. And in fact, it can be conceptualized as a prediction pyramid, as proposed by Dr. Babushka, Dr. Owen, some time ago, that we need a hierarchy of different scenarios to predict the quantity of interest. That is normally that is unobservable. For example, in our case, we don't have data for this, and we want to extrapolate using our model and the validation data to predict an unobservable quantity of interest. And this is what we are trying to do step by step, but the validation scenario needs to be designed for each parameter itself. All right, a quick demo of the OPAL.
So is this scenario modeling context?
Modeling and experiment.
Modeling and experiment.
So technically, in this case, we use more complex scenario as validation. That is more close to the prediction scenario.
Okay.
So let's say
it's a phenomenological context or physical context.
It's a domain and boundary condition and whatever it is.
So in other words, like I would expect that there's, MD works in some context, a continuum model works in a different context, and it could be equations and it could be a simulation. So these two together are a scenario in continuum scale and the microscale and the atomistic scale.
Yes, both
Okay.
of them, the way that you pose both of them, set of boundary condition or something that you put on there, that considered as scenario.
Okay, thank you.
So let's say you want to predict the behavior of the airplane wing. The experiment that you have, small scale calibration, is a uniaxial test, right? But when you go to validation, then you cannot just do uniaxial. You need a different scenario that represents a little realistic behavior of the prediction scenario, which is the thing.
So sorry, then I'm misunderstanding. So then this is like a level of idealization is a scenario? Like this uniaxial would be a very specific idealization of the...
Because you can do experiment
Right.
and you can get the data,
Okay.
right?
Yeah, I'm sorry, just trying to understand. Like,
Yeah.
Thank you.
I'm trying to explain again.
Okay.
But this is also very important, and it's a little subjective because it depends on what experiment can be done.
Okay, thank you.
Right?
But just to clarify, so scenario can be a set of boundary conditions on any type of domain. Observation could be either an experimental observation or the actual solution of the PDE from a model that we have.
Okay. So in this case, observation, that is something coming from discrete dislocation dynamic, right? A stress strain, size dependent stress strain. Scenario, for example, is the size of these grains and size of the film thickness.
But then you have different levels.
Different levels.
So that then a different level is a different experiment or a different simulation.
Different experiments. Yes. Yes. Normally it's experiments. That is the driver, right? What you can actually get data out of it. All right. A quick demo is that we do global sensitivity analysis. It turns out one of the parameters are not sensitive. We assume to be deterministic. We categorize the model based on the number of uncertain parameters. We start from the first category, and it turns out that M2 is the most plausible model. So we put this into validation test. Before doing the validation test, we designed a model-specific validation scenario for this particular case. And the idea is that the validation data should inform the important parameters for predicting the quantity of interest. So this might clarify a little bit. Proposed validation scenario. We have the same domain for the discrete dislocation dynamics. The changes is the amount of deformation or applied strain that is applied to this domain. That leads to an observation, right? And remember that prediction scenario is that this complex thing, and this is the quantity of interest. Now, how we enforce this? We conduct parameter sensitivity of all these three different proposed validation scenarios, considering model output to be the validation observable. Here is a strain energy. Sensitivity of the prediction scenario, considering model output to be quantity of interest, the one in black. And it turns out that the sensitivity of the parameter in SV2, the one in red, is in the range or higher than the one in prediction scenario. So this is the scenario that actually informs the parameters that are important for predicting the quantity of interest. So we keep that for creating the validation data. We recalibrate model M2 using the designed validation experiment, and by doing the validation test, we basically predicting the model prediction compared to the observable. Basically, here is a strain energy. It turns out this is not less than a tolerance, and the model M2 is not valid. If we go to the next, we need to do the same steps in the next step in the Occam category, and it turns out that M4 is actually is the most plausible one in this category, passes the validation test, and we deem that that is optimal predictive. Technically, OPAL terminate at this point. However, Here I did a little more simulations here because we have only 3 more models, and it turns out that actually if you make the model more complex, if you look at the validation metric, doesn't mean that it does a better prediction for you. And I mean, if you look at from the continuum mechanics, these are kind of obvious. We have 2 length scale here, and then we have this hardening that doesn't get informed. But in general, the point stands here. So now we have our optimal predictive model. We can make a prediction of the complex physical system with the level of confidence that we get in the prediction and everything. All right. So this was on physics-based models. There are lots of scientific machine learning-based surrogate models these days, in particular neural networks that create a surrogate of parameter to observation maps at lower cost of the physics-based models, and they facilitate larger scale problem for uncertainty quantification, inference, and optimization. But the fundamental challenge is that as we say that we don't have enough experimental observation, if we are dealing with complex physical model, again, we afford only a small data set. And the traditional training and testing empirical validation or trial and error architecture selection may not account for the uncertainty or reliability of the prediction. And what I'm thinking, and I'm trying to go to this direction, is that as we need validation and uncertainty quantification for physics-based models, why not we apply more rigorous approach for the surrogate modeling, as we are using those extensively these days for making prediction of critical decision, basically. What we are working on is on Bayesian neural networks, and to create a surrogate for basically a toy problem at this point. But I'm also looking into Bayesian convolutional neural network and hopefully at some point neural operator. The idea is that we define Bayesian neural net model, not only the architecture, but form of prior and likelihood. So we have different parameters here, network parameter, weight and biases, inference hyperparameters, variance of the prior, for example, how you model the noise basically, and architecture hyperparameters. There are other hyperparameters, learning rate and so on, that we are not currently looking into. But the way that we determine those parameters is through hierarchical Bayesian inference. And this is in a very old classical paper of McKay, 95, which surprisingly, after all these efforts on the machine learning, nobody actually looked at this paper and the importance of it. We are not dividing anything for testing set, but we are using the entire data. If we have a set of possible model, different type model parameters, at different level, we determine basically network parameter, hyperparameters, inference hyperparameters, and basically posterior plausibility. At each stage, the evidence is the likelihood for the next stage. And basically, the last one leads to architecture selection. So this is the version of OPAL for surrogate modeling, or Bayesian neural network type surrogate modeling. It looks very much the same by categorizing the model and basically going category by category. But there are, you know, that now we are dealing with a huge possible, basically possibility of the model space. Our model space is huge. How many layers, how many connections, how we can search there. So many of the technical stuff are completely different here, as well as the validation. I'm just again showing you this, that let's say our goal is to do uncertainty quantification on this material. We are doing it with finite elements. Our assumption is that it's too expensive. We cannot do UQ. So we try to get data from smaller scenarios, and which one the validation scenario kind of represent the prediction scenario, and using this data to extrapolate. Obviously, we are looking into the uncertainty that we get, errors into extrapolation, and how basically optimize the architecture to do a better prediction for us. I mean, the paper is not out, and I don't have good results. This is just a preview of basically if we are doing fully connected network and a sparsified network, by maximizing the evidence, how that basically behave with respect to uncertainty in extrapolation. All right. So the second part, I'm going to discuss about a scalable Bayesian inference with respect to high-dimensional parameter space or data space. And the goal here is for personalized cancer treatment. And the overall idea is that we have lots of retrospective cancer data, imaging, let's say tumor, brain tumor. How about we create a predictive model that can predict the tumor in a specific patient and for personalized treatment, for optimized treatment for that specific patient instead of using it as instead of a standard approach that is applied to all the patients based on some variability. All right, challenges, we have a scarcity of patient-specific data. We have one or two imaging time point technically to make decisions. We have model inadequacy, even physics-based models. It's a complex process. Definitely we have lots of model inadequacy, whatever we do. And the idea is that we have patient-specific tumor shape because the brains are different from one person to another. The heterogeneity is different. That leads to different shape. And that's basically the main part that we want to address here. So our tumor growth model is a PDE, 2 parameters, and the MRI data we are using the rat subjects, basically. And if you are familiar with MRI data coming out of slices, and this is a center slice of the brain that shows through time how the tumor evolves, and we are using that. All right, again, Bayesian inference, we want to determine the parameters. Parameters are theta, d, and g, 2 parameters, but now to account for the tumor heterogeneity, we consider those parameters to be space-dependent, especially varying parameter. And we discretize those with finite element methods in the finite element niche. Now we have a high-dimensional problem, leads to curse of dimensionality. Basically, this high-dimensional problem, if we are doing the regular method, then it's impossible to infer all these parameters at the same time. All right, so in our setup, our prior is a Gaussian random field with maternal covariance that can be cast, and this is similar to GP and everything, but this that comes with a special correlation length. And this can be cast into a set of PDE to be solved. Likelihood function is a simple Gaussian additive noise between the MRI data and model output at each point at each time. We came up with 2 scalable Bayesian inference. One of them is Laplace approximation, or LA, to the posterior. This is based on linearizing the posterior distribution around map, and basically leads to the fact that the posterior is Gaussian, centered around the maximum posteriori with a posterior covariance matrix. Theta map can be found through deterministic inverse problem, PDE constraint optimization. There are lots of methods out there already. But for posterior covariance, this is a huge matrix. And technically, this can be written as the inverse of the Hessian of negative log likelihood and effect of prior. So now what we're exploiting here is a low-rank structure in the parameter space that are well informed by data to handle this large matrix, basically, for the posterior covariance. That is by solving a generalized eigenvalue with respect to prior preconditioned Hessian. And in most of the problems, we have a very fast decay in the spectral, basically in the number of dominant eigenvalues that are exist here, and basically dominant moods that are get informed by data, and we return only the important ones. And this is basically, there is a truncation error for this approximation that we can actually control, right? 5, 10, I mean, based on experience, we can return 10 to 15, but obviously this is something that can be explored. All right, furthermore, this is Laplace approximation. This is Gaussian. We are assuming all the points are Gaussian. This shouldn't be all correct. But we can get the Laplace approximation to speed up a Markov chain Monte Carlo algorithm. That is, we build on PCN, precondition crank Nicholson by Andrew Stewart, and PCN gets the constructive proposal for the MCMC based on the prior distribution. We use Laplace approximation to the posterior to construct the proposal. This leads to scalability, mixing efficiency of the chains, and basically, PCN was space dependent as well, dimension dependent as well. All right, so here are some results. Subject-specific prediction. This row is MRI for 2 different subjects. Basically, this shows our prediction. These data is used within Bayesian inference. The last one, testing set, is left out to see how much we can do the prediction. In these cases, we got overlapping coefficient, dice coefficients of over 90%. Just note that these are actual MRI data. They are not basically synthetic or ground truth data. There are lots of errors with respect to MRI data at the end of the day. So, and comparison with Laplace approximation and GPCN, yes, Laplace approximation do a little underpredict the variance of the posterior. You can see that the samples of the tumor boundary, handful of them is actually shows for the GPCN to be different from Laplace approximation, but then technically if you run it in one single processor, you get 87 times faster simulation. And I will discuss why those faster simulations are important, right, when it comes to digital twin or basically optimizing the treatments. All right, these are scalable methods. We can do this in 3D. And basically, this is the same, the RAT1 basically from the model. And this is the reconstructed, 3D reconstructed MRI data that shows basically how these behave. Again, there are lots of uncertainty in MRI. Okay, this is in the context of batch inference. More realistic scenario is that we get the data from patient and we need to inform our model. And this needs to be done in a dynamic manner. That brings us to the Bayesian filtering. And I do a little bit different results here in the material to make Dr. Buklas a little nostalgic. This is the experiment has been done in the same building that he got his PhD. And this is a uniaxial test on a set of material. And this is digital image correlation system that takes images of this material, correlate between those, basically compute the spatial distribution of the strain. So what you see here, strain start to increase as we pull this material, obviously. But once, if you look at this point toward the end, we recognize a hotspot that leads to failure from that point. And what we want to do is to integrate this data in a dynamic manner with the continuum damage mechanics, which at the state that we want to predict is the damage variable, some value that changes between 0 and some critical value for the failure. So we are doing exactly the same high-dimensional Bayesian inference, now in the context of Bayesian filter for data assimilation. Every time data comes, we update our model, and this is the damage variable, and this is experimental observation, which I'm going to run them at the same time. And you see that after 50 seconds of start of the experiment, we recognize there is something wrong with this point because we have higher amount of damage, while the observational data still in the level of high noises, and basically takes another probably 50 seconds. So now we see basically the hotspot from that corner. So basically what I'm trying to say is, if you do this Bayesian in a filtering manner, in a dynamic manner, it provides opportunity for us to do some prediction of quantities that we are interested in. Okay, so, all right. I'm going to touch base on this optimization under high dimensional uncertainty. And this is in the context of net zero buildings and the requirement for high performance insulation components. We are looking into silica aerogel porous material and their use for thermal plants. These are high performance insulation components to interrupt the heat flow. Silica aerogel, this is something that created by two of my colleagues at UB. It's a lightweight, highly porous material. They also show the additive manufacturing components of these materials, but for this application, they have low mechanical properties. What we are trying to do is to use a predictive model to do this design decision making, basically. And we already have the predictive thermomechanical model from the previous paper. Of course, we didn't do model selection or very rigorous model validation, but let's assume that we already have it. This is the continuum theory of mixture for two-phase materials. All these red parameters are determined already with, from experimental data. What we want to do for design or optimization is basically determine the special distribution of porosity, right? And the idea for this type of material is that you have high porosity, you have better insulation, low porosity, you have better mechanical strength. And we want to see how these basically, they interact with each other to reach to both insulation functionality and mechanical properties. And the source of uncertainty is basically imperfect material property, errors in additive manufacturing, and so on. Okay. So this is a multi-object optimization problem, which means that we have two different objectives that they are working together. And one of them is thermal, the other one is mechanical. Each of them depends on a set of design parameters. Here is porosity space, and the uncertain parameter, which we assume again to be especially correlated uncertainty, because to account for example, additive manufacturing and some practical relation to that. But the computational issue is that again we are dealing with optimization under high dimensional uncertainty, because this is especially distributed after discretization, we get high dimensional. And to mitigate the uncertainty through this design basically framework, we are leveraging a risk-averse cost function. That not only we include the mean of these two objectives, we also consider the variance as a risk measure to basically reduce the variance, basically make the design decision in the space that we have more confidence about the outcomes. And the last term is the regularization. Okay. So this is again the computational complexity coming from the fact that we have high dimensional parameter space. We need to compute mean and variance at each optimization step. If we do Monte Carlo, then it becomes very complicated. At each step, you solve a set of PDEs, 1,000 samples, and that's just one step in the optimization, and you need to move forward based on that. In the general sense, we use an approximation, quadratic approximation, by using truncated Taylor approximation of the mean and variance. And to compute these traces, we exploit the low-ranked structure of the precondition Hessian that leads to dimension-independent cost. Basically, this leads to, instead of doing large number of Monte Carlo sample, leads to solving one nonlinear PDE and handful of linear problem based per optimization iteration. I'm not going through the rest of the details about these. I'm sure that Kira at some point is going to do a presentation for you guys. This paper just came out. That's the main part of his PhD. What I want to convey at this stage is that once we have a predictive model, we can do optimization under uncertainty. There are challenges with each of different version of cost functional when we are accounting for the uncertainty. And problem with high dimensionality. So now I'm going to discuss a little bit about future plan. Where does these things go? We know how to do, at least we have some notion to do validation and selection, somehow integrate imaging data on high dimensional parameter and do optimization. And this going toward predictive digital tool. And there are different explanation, different interpretation for digital twin. There are different terms such as cyber physical systems. But the one that I like and the way that I'm thinking about it is this definition. That his digital twin is a dynamically evolving model of an individual patient, individual plane, individual civil infrastructure that's basically informed by data from its physical twin, and the idea is to drive decision making, right? And this roots in basically aerospace for monitoring and maintenance, the project that I showed on the uniaxial thing that was part of these basically. But nowadays this is a big and hot subject basically for managing, for example, climate change. This is an atmospheric model from European Union for predicting floods and fires. Or basically nuclear digital twin for energy system safety, for NRC. And I heard that there are also some companies that they are building around digital twin. But at least my personal belief is that we are not really there. We are not really actually can create a digital twin of every physical system that we want. And to just show you the amount of interest on this subject is that the National Academy of Science and Engineering created a committee to specifically identify opportunities and challenges in advanced mathematical, statistical, and computational foundation of digital twins. The way that I see it, these are the different components of a predictive digital twin. Consists of physical systems and model. Physical system provides dynamic data that integrates with this model. The model prediction provides dynamic control, right? And from our talk discussion today over the lunch, I know that many of you work on many of these components, probably very beautiful theory for control under uncertainty, or inference, or optimization, right? So I'm just going to list basically applications of the need for making this and basically the challenges that exist here. First of all, the model should be physics-based model, at least from putting my mechanics hat. We cannot just rely on big data. We need big models if we want to do big decisions. Now, if, for example, we are predicting tumor, we cannot wait 3 days for one simulation to be done. Then we might need surrogate model based on scientific machine learning. But either way, we need to do the model validation and uncertainty quantification, either physics-based or surrogate model. Dynamic data model integration, Bayesian filtering, and dynamic model selection. Basically, I want to have this as multiple validated model that go through together and we dynamically pick one. And optimal control, I mean, this is a little old term, and my student tells me that use machine learning and reinforcement learning, same thing. This needs to be risk-averse, multi-object optimization under uncertainty. And finally, this is not a one-way street. If data helps the model can help with optimal sensing and basically model-driven optimal experimental design. Again, I'm not saying I'm doing all of them. I put this out there in the sense that you are interested in these subjects, and maybe we can collaborate. I don't get that much of chance to have bright minds like you guys and your students, and that's why I thought that to make a summary. The application I'm looking into, one of them is MRI-guided cancer digital twin. to basically to get the images from a specific rat, Mrs. Rat, for example, and through time that provided to our digital twin to basically predict and optimize the radiotherapy regimes for this specific patient, specific subject. This is tailored to NIH and in more practical sense, but we're also looking into advanced manufacturing of nanomaterial to control the laser for directed self-assembly of blood copolymer. This is more into methodological developments and use of the surrogate model and use the physics-based model as to generate synthetic data. All right, so this brings me to some concluding remarks, going back to model selection and validation. Sometimes those things come confused with this statement that the complexity of the model should align the available data. If we use simple model when data is limited, this leads to dangerously overconfident prediction. So we are relying on Bayes' theorem that the choice of model is not based on amount of data, but it's based on prior belief that we have on the model parameters and the model itself. And another thing is that basically the Occam-Plausibility Algorithm, those strategies are just a blueprint. You are not trying to remove the modelers outside the loop. And many of the decision needs to be made for implementing those strategies that are subjective decision to the model, such as model complexity, validation tolerance, and so on. And at least I believe that confident decision making in complex physical system demands advanced methodology algorithms to address the model validation and uncertainty quantification challenges. At the end, I would like to thank the graduate student, Pratyush and Ajaru, my current students, and Kira Jingyatan that has done most of these simulation, and Baoshan Liang, the master's student that she has done the tumor stuff, and collaborators basically from San Diego National Lab, UT Austin, and University of Buffalo. And at the end, these are the related publications. And I mean, as I made, and I was making these slides, I keep thinking about many of these, the foundation of these approaches, this methodology that I showed you, they rely on these two persons, founding fathers of computational mechanics. Unfortunately, we lost both of them this year, but their work, their influence in model validation, uncertainty quantification endures for years to come. And I would like to thank you again for your time and attending this presentation, and I would like to take any questions next. Thank you.
Any questions from the audience?
So, can you give a little bit more detail about this MRI-guided cancer digital twin?
Oh, I'm happy to. We just submitted the resubmission, so everything is in my head. All right. So, first of all, we have some historical data that, for example, that mimics the historical data that we have from cancer. We use that within that OPAL thing to calibrate and validate and select the model that we use for prediction, right? Then we determine the initial parameters because we have scarcity in data. We determine the parameters and basically create the prior distribution for the digital twin. Now we get Mrs. Rat, a particular rat that we haven't seen. We get the MRI data. Those MRI will be provided to basically our digital twin, which is initialized based on retrospective data. And the idea is that we use that basically to optimize the treatment. And the treatment is two things: decline the tumor burden and minimize the toxicity of radiotherapy. And we do it in fractionated radiotherapy. Is that kind of?
So is part of the model selection process involve figuring out what type of tumor you're talking about?
No. We are focusing on one type of tumor,
What type of tumor?
one type of sex that is just female. And in general, what we said is that you need different digital tuning for example, men, women, different type of tumor eventually. But no, we are not going to change anything there. This is just predicting the tumor shape, and based on that, the optimization of rate.
One more question.
Sorry, I didn't quite follow something early on there. You're looking for the simplest model that provides good predictions, if I understand
Yes.
correctly. Is it possible, or does your framework allow you to do that sort of sequentially starting from the simplest model without having to implement the more complicated ones?
Well, this is basically that, I'm sorry, maybe I rushed through it. That is the notion of different categories, right? The category, low categories, they have simplest model there. But as we move up, we add more models into play, right? However, that can be applied. Okay, so the way that we think about it, what is the measure of complexity? That is a subjective decision, right? Here we are assuming the number of uncertain parameters, which means that we do sensitivity analysis, we assume some parameters are deterministic, rest of them drive the complexity. But this is very subjective decision, right? This depends on what computational resources you have, what code you have available. I mean, honestly, solving ODEs is far more complicated for me to solve a PDE. So I would like to go to, that's why the subjectivity comes.
Yeah, I'm perfectly fine with that. I deal with those kinds of things. What I have in the back of my mind is, let's say I solved just an ODE, and I didn't have any PDEs, I didn't have anything else, right?
Mm-hmm.
Just the ODE. Could I use your techniques to then say, this one is good enough, I'm done. I'm not even going to bother with the next one.
Yes.
Love it. Thank you.
Yes.
But this is what you said, right? You stopped at some point.
At some point you stop,
Okay.
if you pass the validation.
And your universe is just the models that are simpler than the ones you've currently
Yes,
got. Okay,
yes.
thank you.
I stop there. However, if you have a family, you go through it, none of them are valid, then that has another loop. I mean, obviously I didn't explain, that you expand the model, right?
Thank you, I understand.
So what is the stopping criteria now, like to find out, okay, this is the model that you're going to kind of conclude kind of a thing, like in your case?
So, this is a very, very important question. When,
Because
Yeah.
it's data specific, right?
this is model specific data,
Okay.
right?
Okay.
And the way that we set up for physics-based model, not for machine learning, that's different. Right? You are doing different type of validation, leave one out or something. But for physics-based, because they are stiff, they are not really capture the data very well. The way that we are doing it is the distance between validation observed. This is coming from data, this is coming from the model. That should be less than a tolerance. What is this tolerance? That's a subjective decision, right? The tolerance that you use for tumor model is different from the tolerance that you use for, I don't know, design a chair, right?
Okay.
You are making life and death decisions versus you are selling some stuff, right? So these are different things.
Any other questions?
I have a general question. So in your concluding remarks, I think the first statement seemed kind of counterintuitive to me. I was wondering if you would go back to it.
Okay. Okay. So let me tell you the background where I'm looking at this, because I'm coming from engineering environment, right? Many of the applications, especially medical people, they said that no, we don't have data, we don't need complex model because we don't have data, right? So, and you see that we are using the data to select the model. But I want to make sure that we are not saying if we have a limited data, then we definitely need to have a simplest model. No, that needs to be go through the process, check the validation on it. You can have complex model, small data, but it gets informed, right? That's what I'm trying to say. Okay. Is that clarifies?
I think so. It just seems hard, the converse, it seems very hard to say, oh, we should have a really complicated model, even though we don't have very much data, because then, you know, how are you going to choose parameters?
So I think the way that I'm trying to say here is that they need to go through the process of validation and checking. You cannot just throw away some models by just looking at it and say that, no, these are too complicated. Cancer doesn't work like that.
Okay,
Right.
yeah, I think I understand.
I don't want to do that. Don't want to make an excuse that, oh, we have a limited data. We always have limited data. We never have sufficient data. I don't think from physical system we have a complete set of data, right? Even if it looks large enough. But I don't want that to be made as an excuse to throw away some of the good theories.
Okay. I think with that we can conclude the talk for the day. I thank our speaker one more time.